My name is Nick Leaf. I and my colleague Max Rietman are both developer technology engineers at NVIDIA. Today, we're going to be talking to you about high-performance remote scientific visualization in Jupyter notebooks. I originally come from a scientific visualization background. When I first learned about Jupyter and all the things that people are doing inside of it, I wanted to figure out how I could replicate some of the scientific visualization I had done previously in the Jupyter environment. So when I first started researching, I initially came across the diagram I'm showing here of the whole Python visualization landscape. You can see that it is pretty extensive. There are a lot of different tools. Many of them are fairly single purpose, but are designed to work really in Jupyter and work well. But it's difficult coming from a scientific visualization background to know exactly what tool will do what you want. Another question you might have run into is if you are an existing ParaView user and you're comfortable with a ParaView based workflow, which of these tools will let you replicate that workflow inside of Jupyter without having to go through the trouble of, say, saving your data from Jupyter to disk so that you can load it up in ParaView externally. Another group of people that I wanted to serve are existing Jupyter users who may be hearing about ParaView for the first time or maybe have heard of it but aren't terribly familiar with it. If you're a Jupyter user or a data scientist and you happen to have data that would be very suitable for existing scientific visualization tools, some of the existing Python visualization packages can do a very good job with that type of data, but it may not do everything you want, or maybe you've heard of a specific visualization technique that's only available in ParaView. Another issue you might have run across is most Python visualization tools are designed to load the data from the server, the Jupyter server, wherever that's running, to your client browser and then render it locally. If your client is running on, say, a low power laptop or a thin notebook of some sort, it may not have the graphics power that you're looking for to visualize your data, or your data might be particularly large and loading the entire raw data to the client browser isn't feasible. There are tools that can do server-side rendering. Data Shader's the best example that I know of. But Data Shader also isn't designed to do very fast, highly interactive rendering. So to kind of serve that need, we created IPyParaView. This is an open source custom Jupyter widget, so it is built on the existing Jupyter widgets framework. It runs ParaView using the Python bindings for ParaView directly in the notebook. This allows you to load up your data, visualize it using a ParaView pipeline, and then interact with it and control it in 3D directly in your notebook without having to save the data out or anything. This is all rendered on the server, on the Jupyter server itself, by the way. And then finally, it allows you to, in Jupyter, have access to an RTX-powered ray tracer to visualize your data and get some really cool looking effects. So the little example I'm showing here is just a CT skull dataset that was loaded using NumPy, transferred into ParaView, and then we're adding some lights and some other nice effects. So let's go ahead and look at a quick demo of how ParaView actually works inside of a Jupyter notebook. So this is a Hello World style notebook that we created. The first thing we have to do is set up a simple ParaView pipeline. So these first 4 lines of this very first cell here are that ParaView pipeline. We import the paraview.simple package. We create a simple sphere object. The sphere has a certain number of subdivisions along the longitudinal and latitudinal axes. So this would be a triangle mesh of a sphere, and then we apply a shrink filter to shrink those triangles and just make them a little smaller. Once the pair view pipeline is set up, we create a PV display object which we import from the IPI pair view widgets, and then we display it. So if we run that notebook cell, you can see we get a pretty standard pair view output. That's kind of what we expect. But we can also mouse over and interact within 3D. So all the typical mouse controls you'd expect are available. This is again all running on the server and streamed to the browser. One of the big advantages of running in the IPI widgets framework and the Jupyter framework is that we have access to other IPI widgets to control our pipeline. So for instance, let's say we want to interactively set that shrink factor using a slider. We create a little user-defined callback function that will set the shrink factor and then use interact from IPI widgets to spawn a slider for it. So you can see as we control the slider, it changes the factor by which those 3D mesh elements are shrunk. We're not limited to just a single PV display object either. If we have a different data set, or if we want to just take a different view of the same data set, we can create a second PV display object. So here, we set up a slightly different pipeline that uses a wavelet data source, which is just kind of a 3D sinusoidal type data, synthetic data source. And then we're using a contour filter to compute an ISO surface of that data. So this tells us a little something about the shape of that synthetic function. But maybe we're having a little trouble deciphering what that shape is. It would be helpful if we had some more cues to help us learn the 3D shape. Earlier I mentioned that we have access through PairView to the RTX-powered backend. And we can just turn that on with a couple more lines of code. And there you have it. This is a fully path traced 3D data running in a Jupyter notebook, running on the server and streamed live. So very briefly, without going into too much detail, I want to describe to you how this functions under the hood. The way all Jupyter widgets are set up is they have a front end and a back end. The back end is what runs in the Python kernel. So that's where we create that PV display object, and that's fully accessible to the Jupyter user and fully accessible to your notebook. So that's meant to be scriptable and modifiable. The front end is written in JavaScript. That's what's running in your client browser. And ideally, you should never have to muck around with that. The idea is that that's all done for you, taken care of for you, and you don't have to worry about it. For the way this works in a technical fashion, that background widget is running a Python background thread that will do a render loop and continuously render the data. As frames are rendered, they are placed into something called a traitlet, which is basically just a buffer that gets synchronized between the front and the back end. So automatically, every time a new frame is rendered, it's sent to the front end. The front end displays that image using the JavaScript, and then any interaction events, say mouse dragging to rotate, will then generate messages that go back to the back end, which updates the camera and renders a new frame. So you may have noticed that in the front end there is a widget model and multiple widget views. One nice feature of Jupyter widgets is that the widget model corresponds with the backend Python object. And there's only one of those because you don't want to necessarily have to replicate a bunch of data every time you spawn a new PV display. But you oftentimes want to display the same widget twice. Say if you spawn a widget, visualize your data, and then do a whole bunch more work to manipulate the data and want to view that same data again later on in the notebook, you can just spawn a new view of it. So that's all for the quick, simple example, and hopefully that gives you an idea of how IPy Pair View works. Now I want to turn it over to my colleague, Max Rietman, who's going to dive into a more complex, more complete example.
Thanks, Nick, for the introduction. So, like he said, my name is Max Rietman, and I'm going to demo for you today this notebook and the pair view features, but looking at a more machine learning context using the algorithm UMAP, which is provided by the Rapids library QML. It provides a highly optimized UMAP implementation. And so let's get started. So here we have a standard sort of import cell. So we have NumPy, QML, a number of numba, pandas, plotly, and matplotlib to compare against iPairView and our IPy PairView imports, and all the standard stuff that you would need. So we're going to look at first the MNIST dataset, which is a dataset of handwritten digits. And in this case, I'm using the full resolution data set. So we have 28 by 28, making for 785 features, 20 by 28. And we can see here that we have we have 60,000 different digits we can look at and just poke around and see different digits. So that's to visualize them. So let's go ahead and try UMAP on them. So UMAP can embed from very large dimensions to very few dimensions. So in this case, we're going to go from 785 dimensions down to, let's try it first 2, and just use matplotlib and see what the scatter plot looks like. So QML has a little warm-up time. The first time you run it, it's a little slower. So it takes about a second to run the 60,000 data points with 785 down to 2 dimensions. And so let's go ahead and visualize what this means. And then the embedding will be very clear now once I do it. So here we see each digit has a color, and they're embedded into little clusters, perfect little clusters, which would be very easy to set up an inference or machine learning pipeline from. And so obviously this works very well. This data set is known to work well, but maybe we want to try in 3 dimensions. So let's go ahead and set 3 components here. Again, it takes about a second to run on a GPU. And let's go ahead, but this time instead of using matplotlib, we're going to use plotly, which is a JavaScript-based plotting engine. And it takes just a moment to get the plot set up for these 60,000 points. And as you can see, it looks pretty nice. It's interactive. You can zoom in and out. You can see the different shapes. And as you can see, the 3D embedding does work quite well. It gives the embedding, the UMAP, a little bit more room to breathe to set up good clusters. And so the only thing is we notice, one, it's hard to tell exactly each individual cluster. If the shape of them was important, it can be difficult to know what the shape is unless you really move around a lot. And the second point is that all of these points had to be transferred to the browser for visualization. So if this was, let's say, 6 million points, which would be relatively well handled by PairView, it won't be handled very well by JavaScript. So one, it would take quite a while to transfer, and then I think JavaScript would probably have a hard time visualizing, particularly if you're on a low-powered notebook. And so you can have a very high-powered server in a rack somewhere across the globe and run your experiments on a tiny little notebook somewhere else. So let's go ahead and try this out. So we're going to have let's set up the pair view. So our pair view pipeline can be made, can use data frames to ingest the data, so you don't have any sort of funny conversions to text or back. So straight data frames. So we'll go ahead and put the data in a data frame. And I have a scatter 3D plot that I built that hides away some of the pair view. I set up a ray tracing checkbox. So as you can see, when I'm using ray tracing, I enable some settings in pair view, enable ray tracing and how many samples per pixel. And then when I can turn it off, it just turns it off. So let's go ahead and set that up, get our widget going, and go ahead and this is just using IPython widgets. And so here we have a checkbox for the ray tracing. And so here we can see already that having the pair view looking at these clusters is already quite a bit easier to tell what's happening from compared to iPlotly. And now let's go ahead and turn on ray tracing. And here we can see already how much dramatic the difference can be. So we have shadows, we have reflections in the background just for fun. We have lighting coming down and creating shadows, both on the ground and inside of the little spheres. And we can even play around with other things like ray tracing. Generally, we have depth of field support, so we can enable depth of field. And okay, so we see now we're a little bit out of focus, so let's increase our focus. So now we see we have some points in focus, and other things are blurred. Let's play our experiment again, so we can see how we can actually control and then let's increase the depth of field again, so we can really control our visualization and play around a lot with different features. So let's turn off ray tracing and have another look. And let's maybe toggle it on once or twice to really see how much clearer, like this object here, you can really see the shape. And this one maybe too, you can really see what the texture looks like. And it's more clear that there's a certain depth to the shapes themselves. And let's go back, we can even go look up here. So this is the same data. And you can see how much more dynamic this looks. So let's try. So this UMAP is MNIST is very well known to work very well in embedding the MNIST data set. So let's go ahead and look at a more challenging data set that has more data, so 750,000 points and about 500 features. And we'll go ahead and load that data. Let's go see how long it takes. So we're going to run 10,000 rows. So about 700 milliseconds. Maybe try one more time to see 600 to 700 milliseconds on this GPU while running the screen recording. And here we're actually going down to 4 dimensions because we wanted to have a little bit of room to play around with in pair view. And so we can just go ahead and take a look here what this looks like in Matplotlib, and you can see, especially without interactivity, we don't really have much in the way of. It's difficult for us to know what's wrong or what's happening. We have no depth cues and nothing like that. So we're going to go ahead and set up the pair view visualization. So here, this code here sets up a callback, which allows us to actually view the iterations of UMAP itself, which is maybe useful for the developer of UMAP. And we're going to set up our pair view plot, which has a few extra features from pair view. Set up our callback, and so instantiate our callback. And here we have some functions that are just setting up interactivity. So these are just IPy widgets, so some sliders, some checkboxes, some text entries for controlling our visualization. So I'll get our widget created. Here we go. So now it's setting up all these little checkboxes. Actually, it runs the UMAP every single time. And so let's get scrolled out. So here, and actually it seems like our spheres are a little small, so we go ahead and play around with the sizes there, and that's actually a little bit better. And let's maybe increase our number of data here. So this should take, yeah, look kind of neat, huh? So we actually get, we can see the algorithm as it iterates its way towards things. So that looks pretty interesting. Okay, so here we have the data, but it's somehow the clustering, it seems like it's working, but it could be better. So why don't we go ahead and try some of the hyperparameters. So UMAP has several hyperparameters, 2 of which I've exposed here. So there's number of neighbors and min-dist, minimum distance. And these, of course, have intuitive explanations, but maybe the easiest way is to just play around with them a bit to see what we get, to get started, to build a little intuition for what might work and what doesn't work. So let's go ahead and try min-dist. Let's try like 0.5. Okay, so that could be better. And let's try, say, 0.9. Well, that already looks quite a bit better, I would say. And let's try like 1.6. So that seems maybe worse. Let's go back to 0.9. Okay, so now we have our visualization, but let's turn ray tracing on and see what it looks like here. Let's go ahead and fix our depth. There we go. And so, okay, this already looks pretty nice. Pretty good embedding. We have ray tracing. And so one interesting thing we did here, because we have 4 dimensions to play around with, I wanted to have some additional sliders to show off some of the pair view visualization tools. And so we can, I've created slices into the 4th dimension. So we have a slice width and a slice position. And these are using pair view terminologies. There are thresholds. So we can go ahead and increase the width and see more of the data. Or we can decrease the width and see less of the data. And then we can go ahead and slide through the data. And it's pretty interesting. Let's go ahead and look at all the data. And then now let's, yeah, so that's that. So now we can really see how much easier it is to see our data, especially if we zoom in a little bit. So let's go ahead and decrease the focus distance so we get a little bit sharper image. And we can toggle ray tracing on and off. So we really can tell that it's really dramatic how much dynamic shadows and ray tracing bring to the visualization in terms of understandability of what's happening inside this shape. So let's go ahead and toggle that a couple of times just so you can get a feeling for it. And if we compare, so let's go ahead and put this back to 0.1. Oops, there we go. So that's what this looks like. And if we go back up, and this is what this looks like. So you can really tell, like, qualitatively, we kind of see that there's some sort of thing happening, but compare that against this, it's really amazing how different it is. And so this makes this much more interesting to play around with, and brings a lot of understanding to the table. So that is the end of our demo. That concludes our demo of visualizing UMAP embeddings or clusterings inside of a Jupyter notebook using our pair view widget. And I hope you could see that the combination of pair view and our new RTX extensions in pair view really enable next generation visualizations of 3D geometries, either coming from more scientific applications or more machine learning or data science centric applications. As we mentioned before, the IPy pair view widget that we saw in the notebooks is available under the NVIDIA organization's GitHub account, NVIDIA/IPy pair view. On that GitHub, there will be several examples, including the ones we saw from Nick and a visualization of the MNIST dataset, which we saw a version of just now. Obviously, the README on the IPyPairView repository will include instructions on how to install it and use it. And I hope you check it out sometime soon. Thanks for watching.